Hello, this is my lab report for Lab 3. This lab focuses on analyzing and predicting the trajectories of objects orbiting around the black hole. To do this, we will be separating the gravitational force into parallel and perpendicular components. We will be using the rate of change of momentum, or Newton's second law, and the position update formula. We will be analyzing the orbits and the escape speed. Our first model focuses on analyzing the trajectory data of a star orbiting a black hole to calculate the mass of the black hole and visualize the force components. Our second model focuses on visualizing the orbits of a planet and a spaceship around the black hole. A brief summary. So we found that an object's speed plays a key role in if it will stay or escape in orbit. The mass of our theoretical black hole is 2.2 times 10 to the 34 kilograms. And if there's an object A orbiting object B, object A will follow an elliptical path. Here are our key principles. We can separate F net into the rate of change of momentum over the change in time. We can then separate this further into the parallel and perpendicular components. Parallel is parallel to the current trajectory of the object, and the perpendicular is perpendicular to the current trajectory. On the bottom, you can see a figure that visualizes these two components of an object orbiting another object in a clockwise direction. And then on this page, we also have the formulas for the force due to gravity, the magnitude of the force due to gravity, and the two position update formulas. For both models, we will assume that the black hole is stationary. This is because the mass of the black hole should be so large that any gravitational force from the planet, spaceship, or star should be negligible. And then we'll also say that gravity, the gravitational force, is the only force that we are concerned with. For Model 1, the system is a star and the surroundings are the black hole. For the first set of calculations in Model 2, the system is a spaceship, surroundings are black hole and planet. For the second set of calculations, the system is a planet and the surroundings are the black hole and the spaceship. For our initial conditions, t equals 0. In Model 1, the initial position and velocity are determined by a random seed. In Model 2, our initial position is determined by the orbit radius and the radius of the planet, which are 1e10 and 1e8 respectively. For the ship, the initial velocity is determined through testing, which we will discuss later. And then for the planet, the initial velocity is 1.2 e7 in the positive y direction. For Model 1, we first calculate momentum using p equals mv. Then we can calculate change in momentum over time, and then also dp dt parallel. Using dp dt parallel and the total dp dt, we can calculate dp dt perpendicular, and that gives us all of our parallel and perpendicular components of the force. Next up, we calculate the mass of our black hole using the formula for the magnitude of the gravitational force, and then we update all of our positions and visualize our arrows. And at the end, we will print the mass of our black hole. For Model 2, we first have our initial conditions, and then we repeatedly calculate the force due to gravity. And that is equal to negative g times big M little m over r squared multiplied by r hat. So we do that and then add up the net force for the planet and the spaceship. And then we go through the position update formula to update the position of our planet and spaceship, and then we finally visualize that trajectory. In Model 1, we found that the mass of our black hole was 2.2 times 10 to the 34 kilograms. And in Model 2, we found out that if we were going fast enough, we could escape orbit. Some potential sources of error: we could have had smaller time steps, and there is still a potential for some coding or model logic mistakes. There is no practical difference between rate of change of momentum in its components and force in its components. mv squared over time is equal to mass times acceleration. Here's a video of our solution to the what-if problem. The velocity needed is shown on the screen. In conclusion, we found that the mass of our theoretical black hole was 2.2 times 10 to the 34 kilograms, and that depending on our initial speed, we can either stay or leave orbit. And if we do escape orbit, then we will move in a straight line.